Today we're going to look at compositions of functions involving inverse trig. Okay, so when we look at the sine function and its inverse, or the cosine function and its inverse, typically the relationship with inverses is that they undo each other. Now, what's kind of unique about these trig functions is remember that we've restricted the domain of the inverse function. So there's conditions as to when they actually can undo each other. So let's talk a little bit about domain and range before we really get into this. So let's think about the sine function, for example. When we just think about y equals the sine of x, the domain we know is negative infinity to positive infinity, and the range is -1 to +1. So when we think about sine inverse, then we can flip this to where the domain becomes -1 to +1. But remember, the range is what we restricted. We can't go forever up and down the y-axis because then we get this fail of a function here. So instead, we restrict the range to be from, and it's inclusive, -π½ to +π². Okay, so this is a direct switch. This is kind of a switch. We have to restrict that so that we still have a function. But remember, the inverse relationship is that the range of the original function becomes the domain of the inverse. So that is where this information comes from. The sine and the sine inverse only undo each other if it fits the domain and the range that we need. Okay, now here's how we need to think about this. We always have to be able to work from the inside out when we do a composition. And this is a composition because this is the same as like f of g of x. In this first example here, g of x is the sine inverse, f of x is the regular sine. Okay, that's what a composition is. And so if we want to do sine of sine inverse of x, those only undo each other and give us an x if x is between -1 and +1. Now, why? Well, first, we have to be able to get through this filter. So when we plug a number in to sine inverse, the only numbers that we're allowed to plug into sine inverse are answers between -1 and 1. Okay, so that is why those are the only numbers that we can plug in. That's why this is only going to be true for values from -1 to 1. I can take the sine of anything. So once I get through the inside function, it doesn't matter, but I do have restrictions on the inside function. Now, if I do this in the opposite direction, it's different. When I take the sine of x, that has a domain of -infinity to +infinity. I can take the sine of anything that I want, but the only thing that I can get out of sine inverse is -π² to +π². And so this is only going to give us x, like they only undo each other if x is between -π² and, whoops, +π². Pause this. Sorry, I was going to sneeze and I meant to pause the recording and I ended up stopping my screen share by accident. So the rule is very similar for cosine. Cosine and cosine inverse, the cosine of cosine inverse, those undo each other if x is between -1 and 1. Cosine inverse undoes cosine as long as x, there's the bell, is between 0 and pi. All right, with tangent, the tangent on the outside, they undo each other for all real numbers. The inverse on the outside only works for the restricted domain, okay? Now, these are hard to remember, and there's not a real good way to do it, okay? But really the question here is, are we allowed to undo each other? That's what it comes down to. So find the exact value if possible. Alrighty. So number 6 says, find the exact value of the cosine inverse of 0.6. Now, the first thing we have to check is, can we do the cosine inverse of 0.6? Now, remember, this 0.6 is a ratio. Whenever we do our sine and cosine, we say the sine of an angle equals a ratio. Remember, theta is an angle. But when we do the inverse, it's the reverse. We do the sine inverse of a ratio, and that has to equal theta again, which is an angle. The ratios must be between -1 and +1 because that's where the unit circle goes. So 0.6, that is between -1 and +1, so we're good. So if I want then the cosine of the cosine inverse of 0.6, that fits the rule. So the answer is just 0.6. Essentially, the cosine and the cosine inverse undo each other, and we just get 0.6. Okay, now B wants to know the sine inverse of the sine of 3/2. Now, the rule for sine inverse is we're doing the sine inverse of a ratio. The ratios have to be between -1 and 1. 3 pi over 2, pi is about 3. That's closer to like 4.5. So that doesn't work. So for this one, since 3/2 is not in -1 to 1, the property fails. That doesn't mean we can't do it. It just means we have to do something else. So now we have to work this out one piece at a time. What we learned by this information is that the answer is not just going to be 3 pi halves. It's going to be something else if it's possible. So we try it first. The sine of 3 pi halves is -1. The sine inverse of -1, remember this is equal to -1. The sine inverse of -1, based on the rules we have to use, is negative pi halves. So that would be our answer. Okay. Remember, sine inverse can only be chosen from negative pi halves to positive pi halves. Negative pi halves and 3 pi halves are coterminal, but we just have to name it differently because of the domain restrictions. And if we look at C, again, the question is, do these undo each other? Can the answer just be 1.5? And in this case, the answer is no, because the cosine inverse is plugging in a ratio. Once again, the ratio must be between -1 and 1. This is too big. So the cosine inverse of 1.5, this value does not exist. So the answer to this one is that this one we cannot do at all. This does not exist. Side note, null set, not an appropriate answer here. The null set says no solution. This is not an equation, so null set is not the right thing to write. So that's the tricky part. What I want you to take away from this is that you cannot always cancel out cosine and cosine inverse. It depends on the numbers we have. And I think that this idea here of thinking about the angle versus the ratio is always going to be important. And that's an easier way to remember it than memorizing the rules. Okay. All right. So moving right along then, these are a little bit easier. When we mix the functions together, obviously cosine is not going to undo a tangent inverse, but we can still evaluate these composition of functions. And what we're going to do is we're going to use our right triangles to set this up. So for number 7, it says, find the exact value of the cosine of the tangent inverse of 5/12. So the first thing that we are looking at This idea of the tangent inverse of 5/12 means that for some angle theta, the tangent is equal to 5/12. So we are going to make a triangle that does that. And so when we set up a triangle and the quadrant, remember with tangent, it's either going to be quadrant 1 or quadrant 4. So since they're both positive, I have to be in quadrant 1. So let's draw a quadrant 1 triangle. That would look like this. Our angle is going to be here. Tangent is opposite 5/adjacent 12. That's the hardest part. So what we want is the cosine now for this same triangle. Okay, the tangent inverse of 5/12, this is equal to theta. So now the cosine of theta, this angle, is going to be adjacent over hypotenuse. So that means we need to first figure out what the hypotenuse is. 5, 12, 13 is a Pythagorean triple, but you can also use the Pythagorean theorem to do that. Now we know that the cosine of theta for this triangle is 12/13. So that means the answer is that the cosine of the tangent inverse of 5/12 is equal to 12/13. So the steps are build the triangle for the inside function, then use that triangle to figure out the outside function. Okay, let's look at number 8. Find the exact value of the sine of the tangent inverse of 3/4. Again, we only have quadrant 1 and quadrant 2 or 4 for tangent inverse, 1 and 4. So if they're both positive, that means that I have to be coming from quadrant 1. So once again, we're going to build our quadrant 1 triangle. Doesn't have to be to scale, obviously. So opposite 3, adjacent 4. Using the Pythagorean theorem, we figure out that the hypotenuse is 5. 3, 4, 5 is the Pythagorean triple. Now we want the sine of this same angle. So sine is opposite over hypotenuse, which tells us the answer is 3/5. Easy enough? Alrighty. Number 9 and number 10, we're dealing with negatives here. So number 9, we want the exact value of the cotangent of the sine inverse of -1/3. Now, remember, sine is y/r, or opposite over hypotenuse. The hypotenuse is the radius, so it is always positive. Sine inverse only gets to choose from quadrant 1 or quadrant 4. So the only way this can be negative is if I am in quadrant 4. So we are going to draw a quadrant 4 triangle for this one. Our angle is right here. So we don't know what the x value is. Sine is y, so this is -1/r, which is the hypotenuse, so this is 3. So the first thing we need to do is use the Pythagorean theorem to figure out the x value, the bottom or the top leg, based on the way this triangle is. And then once we have that, we can figure out cotangent. So pause your video and see if you can finish this one yourself. Okay, using the Pythagorean theorem, the side we're missing is x. So x squared plus y squared, which is -1, equals r squared, which is 3 squared. And whoops, that's not correct. Hold on, let me fix that. 3 squared is not 3, it is 9. And when you subtract 1, that's going to make this the square root of 8, which is 2√2. So let's try this again. Okay, so x is 2√2. And so cotangent is going to be the reciprocal of tangent. So tangent, remember, is going to be opposite over adjacent. So that's -1/2√2. But cotangent, we need to flip that over. So we just get -2√2/1. So that is the answer, -2 square root of 2. Okay, for the last one, find the exact value of the cosine of the sine inverse of -1/2. Go ahead and pause, set up your triangle, see if you can solve this one on your own, beginning to end. Alrighty, so on this one, you do get the square root of 3 for x. And now based on that triangle, the cosine of this triangle is the square root of 3 over 2. Now for this one in particular, you could also realize that -1/2, that's a unit circle value. So the sine inverse of -1/2 when we choose from quadrants 1 or 4 is -pi6. And then we ask ourselves, what's the cosine of -pi6? And you would know that that's square root of 3 over 2. So that's another way that you could approach this one because it's a known unit circle value. The other ones were not, but I always end up setting up a triangle because I think it's easier. So that is how we work with compositions. Focus on the 7 through 10 style problems, but really pay attention to the idea of what's the ratio restrictions, what's the angle restrictions when you're asking yourself about these properties here. And that is where we will stop for today. See you later.